Let's write out the formula for the nth Taylor polynomial for a function, and then we'll use it to find, say, the fifth Taylor polynomial for a function. Here's that formula, and let's use it to approximate the function f of x equals x to the fifth minus 3x to the fourth plus 5x cubed plus 6x minus 2. Well, we know from our formula that we're going to need the first and second and third and fourth derivatives, depending on how high we decide to go with n. I said a minute ago that we were going to find t sub 5, the fifth Taylor polynomial. And that means we're going to need to find at least 5 derivatives of our function. So let's do that here. We have f of x. F prime of x is going to be 5x to the fourth minus 12x cubed plus 15x squared plus 6. F double prime is 20x cubed minus 36x squared plus 30x. The third derivative is 60x squared minus 72x plus 30. And the fourth derivative is 120x minus 72. I haven't given you a b value yet. Let's go ahead and do that. I'll say b equals 0. And I now need to use this formula with these derivatives and this b value to figure out what t5 is. Well, f of b, actually I think what I'll do is I'll write this out as f of 0 plus f prime of 0 times, since b is 0, this is just going to be x, so I'll say times x, plus 1 over 2 factorial times f double prime of 0 times x, plus 1 over 3 factorial, which is 6, f triple prime of 0 times x. I missed something. This is x minus 0 to the first power. The next one's to the second power. So this is x squared. This one's x cubed. And then I have 1 over 4 factorial, which is 24. Since 2 factorial is 2, 2 times 1, and 3 factorial is 6, 3 times 2 times 1. Then 4 factorial is 24 because it's 4 times the previous one. 4 times 3 times 2 times 1. 4 times 3 factorial. So I get 120 over 24. The fourth derivative at 0 times x to the fourth power. I think I'll put this in a box. Otherwise, I'm going to run into myself all the time. So here is my fifth Taylor polynomial, but I don't know what these values are yet. Let's go figure that out. When b is 0, the function, the original function here, is 0 plus 0 plus 0 plus 0 minus 2. So f of 0 is just negative 2. F prime of 0 is this function here with 0 plugged into it. So I get 6 times x plus 1/2 times the second derivative at 0. This function here at 0 is actually 0. So times 0 times x squared plus 1/6. The third derivative at 0 is 30 times x cubed plus 1 over 24 times the fourth derivative at 0, which is negative 72. Let's change this to a minus 1 over 24 times 72 times x to the fourth. And I'll tidy this up now. I get negative 2 plus 6x plus 0 plus 5x cubed minus 3x to the fourth. This is my t5. This is my fifth Taylor polynomial. Notice, among other things, that the degree of this polynomial is 1 less than the degree of the polynomial that I was given to work with, the original polynomial. It's interesting to note that if you graph these two functions, Here is my original function f of x. The scale here is very deceiving, so bear with me as I sketch this. Looks very much like a fifth degree polynomial. This is my f of x, but the scale is, this is about 2 here, so there's 1. But in this direction, this is about 50. So I had to zoom in very much on the y-axis to make it so that you could tell that this was a curve. Otherwise, it looked almost like a line, a straight line. The Taylor polynomial, however, looks something like this. Very similar at around x equals 0. Very similar in the region around x equals 0, but not exactly the same curve. Still in all, the graph of T5 closely matches the graph of f of x around 0, and we could use that for approximating. That's really quite an interesting result. Perhaps an even more interesting result is what happens if we change the place, the location where the problem is centered. Let's say we want to look at this near b equals, I think I'll just choose 2. Then what happens is everywhere there was an x, sorry, not here, in this step here, everywhere there was an x here, this came from f prime of 0, f prime of b times x minus b, right? F prime of b times x minus b. But this time, instead of being 0, b is 2. So this would be, in that case, f prime of 0 times x minus 2. And the next term would be 1/2 times f double prime of 0 times x minus 2 squared, and so on both sides here, right? All the other terms would be similarly affected. Now, but we have to be careful here because I've just said up here, b is not 0 now, it's 2. So that means I'm going to need to change this as well. This is not f prime of 0 or f double prime of 0, it's f prime of 2 and f double prime of 2. So that's going to make this problem look very much like the previous problem, but I have to do some different computations to determine what these coefficients are, right? This is no longer going to be -2. This is no longer going to be a coefficient of 6. So let me do those computations, and I'll come back and show you how they slot in. So it turns out that if I evaluate the function f at 2, I get 34. If I evaluate its first derivative at 2, I get 50. Evaluate the second derivative at 2, I get 76. The third derivative is 126. And the fourth derivative evaluated at 2 is 168. So now I have different coefficient values. And my T5 in this case is going to be f of 2 plus f prime of 2 times not x, but x minus 2. So I'm on this term right here. F of 2 is 34. F prime of 2 times x became f prime of 0 times x became f prime of 2 times x minus 2. I'm about to do this term here. So now I have plus 1/2 f double prime of 2 is 76, and not x squared, but x minus 2 squared, plus 1/6. F prime of 0 was 0, but f triple prime of 0 was 30. F triple prime of 2 is 126 times x minus 2 cubed plus 1/24 x, the fourth derivative of f is at 2 is 168 times x minus 2 to the power of 4. So what have I got here? Move this down a little bit. All right, let's tidy that up a little bit. I get 34 plus 50 times x minus 2 plus 38 times x minus 2 squared plus 21 times x minus 2 cubed plus 7 times x minus 2 to the power of 4. And this graph, let me move my graph back into place here a little bit. This graph looks something like this. Around 2, it looks very much like, my scale is off here, but around 2, it looks very much like the real graph, the actual function we were given. Either side of it, it doesn't look quite so much like that graph, but and it's closer than it is in my sketch here. It's much closer for a much wider range of values than is showing on the sketch. But around 2, it's actually very close indeed. If you zoom in, it looks like about 1.75 to 2.25. The values are going to be so close as to be negligible. The error will be negligible. So the other benefit of doing this, it's not something that, you might wonder, why on earth would you take one polynomial and turn it into another polynomial? In fact, when polynomials are friendly to begin with, why would you change it into a different polynomial? Well, the answer to that question in a case like this is that it gives us some insight into what kind of behavior the function takes on around x equals 2 instead of somewhere else. Here we're looking at, with this one, we're looking at what the behavior of the graph is around x equals 0. But around x equals 2, it behaves very much like this function here. So it's an interesting exercise, but it's also a very interesting way to do an example of how to find a fourth Taylor polynomial for a function. In this case, the function we were given was a polynomial. Let's take a moment and find the error associated with this Taylor polynomial. It's going to be m over n plus 1 factorial. N is 5 in this case, so we have 5 plus 1, or 6 factorial, times x minus b, which is x minus 2, to the power of n plus 1. And simplified, this is m over 6 factorial times x minus 2 to the power of 6. Now, the next step here is to figure out what m is. M, remember, is the largest value that the next derivative, the one that we don't have in our list here, we need one more derivative, the largest power that can take on. Well, in this case, if I just take that next derivative, I have the fifth derivative of x, the fifth derivative of f is 120. So the largest power that m can take on is 120 because it's a constant. So I have m over 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. We know this is 6. We know this is 24. 24 times 5 is 120. Oh, that's going to be very convenient. And then we have 120 times 6. I'm going to write that as 120 times 6 because then I can reduce my fraction. That gives me 1/6 times x minus 2 to the power of 6. But that's m. That's not my error. It's not the largest value that my error can take on. It's the largest value that my m can take on. I'm going to take this equal sign and change it as well. I just realized that should be a less than or equal to. Now, the largest value that this thing can take on, right? This thing has to be bigger than our error. So we want to find out how big can this get? What's the largest value this can take on? And it turns out that is infinity. But if I restrict the region so that I'm only looking at values either side of 2 within a certain window, then it turns out if you graph this function, okay, if you graph this function, you'll see it's a 6th power polynomial. It's very flat across the bottom. And either side of 2, it's pretty good. It's pretty close to 0 for at least a tenth. So let's say that our interval is going to be 1.9 to 2.1. Now, at 1.9 and at 2. If you graph this thing, it looks, I'll just do it off to the side here, around 2. it looks kind of like this. It's very flat across the bottom. And so any values above 0 are going to occur at either of the endpoints. And as it happens, the endpoints are the highest values. Those are 1.9 and 2.1. So if I go figure out what the values are, at 2.1, we have 1.667 times 10 to the negative 7. I'll just call it I'll just write it out, 667 times 10 to the negative 7. And at 1.9, we have, try to get right on 1.9, the same value, 1.667 times 10 to the negative 7. So the value of this function at either endpoint is this number right here. And that number right there is 0. Let's see, 1, 2, 3, 4, 4, 5, 6, 6, 7, plus probably some change, right? And so the largest our error is going to be in this interval is a very small number indeed. If we extend the interval, if we make that 1.8 to 2.2, then our error gets a bit bigger. We get to, it looks like about 1.067 times 10 to the negative 5. That's still a pretty small number. So I can go either side of 2 here for a fairly decent distance. For a given interval, though, in this case, it turns out that this is the error. I could say, for example, find the interval j for which the error is less than 0.01. For error to be less than 0.01. And when I do that, I'm simply going to take this function here and set it equal, not to this value, but to 0.01, and find out what x has to be. And then, as we did with the quadratic estimation, with the quadratic approximations, figure out what x has to be to produce that number, and then we want our error to be less than that, so we round up just by whatever the smallest amount is that we can round up for that x value. So that's what we did. We did that problem, or problems like that, in the quadratic approximation section 2. So I'm not going to do that now, but it's another application of this, another opportunity to explore the Taylor inequality, as we now know that it's called. Something I haven't mentioned before now, although your textbook or your course pack has, is that this, the white Taylor polynomial that I have here, before I started changing it and playing around with it and making it based at 2, it was based at 0. This is simply a special case of a Taylor polynomial. This Taylor polynomial here, let me use a highlighter. This T5 here was based at 2, and this one was based at 0. And when they're based at 0, we call them a Maclaurin. Well, the series would be called a Maclaurin series. But the only difference really is that instead of being based at any other number, they're based at 2. They're centered at, they're based at 0. They're centered at 0. So if the series is based at 0, we call it a Maclaurin series. If it's based anywhere else, we call it a Taylor series. And the series, the Maclaurin series, is just a special case of a Taylor series, in which case it's based at 0. So we haven't talked about series yet. We're not quite there yet, but I did want to throw that name out because you've maybe already seen it in some of your internet research that you've been, I'm sure most of you have probably looked Taylor series videos up on the internet. And it's often mentioned pretty early on that a Taylor series is one centered at any value. And if it's centered at 0, it's given a special name. It's called a Maclaurin series. So that's the only difference there. And we'll come back to that when we talk about series. We're not quite there yet. So let's finish this video. I'm going to do one more example. Okay, so now we know how to find the third Taylor polynomial of a function, or the fifth Taylor polynomial of a function, but sometimes we'll be asked to find the nth Taylor polynomial of a function. So we're going to do that here. This is just example 3.1 from your course pack. It's the same problem done in the course pack, but I'm going to run through it here just to give you a bit of additional explanation as we go along. Let's remind ourselves what the Taylor polynomial is, what the formula is. We have f of b. Actually, I'm going to rewrite this as 0 factorial times f prime of b times x minus b to the power of 0 plus 1 factorial times f prime. No, that should not be a prime. The first one should not be a prime. That's just f of b of f prime of b times x minus b to the power of 1 plus, and it's not 1 factorial. Boy, you get going here. It's 1 over 0 factorial. 1 over 1 factorial. And the next one will be 1 over 2 factorial, which is just 2 factorial is 2 times 1, so that's just 2. F double prime of b times x minus 2 squared. I'll do one more. 1 over 3 factorial times the third derivative of f at b times x minus b to the power of 3. Now, we've been asked to find the nth Taylor polynomial, so we need, give myself a bit more room here, we need an nth term, and that's going to be 1 over n factorial times the nth derivative evaluated at b times x minus b to the power of n. Now, to find the third or fourth or fifth Taylor polynomial, we literally just found our third or fourth derivatives, plugged our b value in, and then stuck those in the positions of the coefficients. And that is, we can do that with this as well, but only to a point, right? We don't know what n is, so we don't know whether we're going to stop at 4 or 5 or 7 or 17. So we need to find kind of a formula for this. Let's go ahead and do the first several terms and see if we can come up with a pattern. Keep in mind that we're dealing with a specific function here, right? We're not just, this is the generic Taylor polynomial for any function f of x, okay? But we're looking for a specific, a Taylor polynomial for a specific function here. So I'm going to start by taking the first, let's see, 1, 2, 3 derivatives. That might be enough, it might not, we'll see. I'll start by writing f of x as 1 minus x to the power of negative 1, because I think that's easier to differentiate than a quotient. And then I have f prime of x is going to be negative 1 times 1 minus x to the negative 2 using the chain rule times negative 1. And that is positive 1. Actually, here's what I'm going to do here. I'm going to move all of this over. That gives me positive 1 times 1 minus x to the negative 2. All right, now let's take the next derivative. The second derivative is going to be 1 times negative 2 times 1 minus x to the power of negative 3 times negative 1, again, because of the chain rule. So I have positive 2 times 1 minus x to the negative 3. Let's go ahead and do at least one more here. The third derivative is 2 times negative 3 times 1 minus x to the negative 4 times negative 1, which is 6 times 1 minus x to the negative 4. Okay, so now I have a first derivative, a second derivative, and a third derivative. I also have my original function, so if I plug b in to each of those, I'll get the value for my coefficients. Let's see, f of b is here, f prime of b is here, f double prime, f triple prime. So when I plug b in, when I plug b equals 0 into my original function, I get 1 minus 0, which is 1, and 1 to any power is 1. This is going to be 1 over 1, right? So that's 1. My coefficient here is 1. And I have b equals 0, so this is x minus 0, so it's x, but it's raised to the 0 power, so that's 1 as well. So essentially here I have 1 times 1 times 1. Here I'm going to have 1 times, now my x minus b, or my x minus 0 here is raised to the first power, so that's going to be x minus 0 or just x. So I'll have times x. But what is f prime at b? Well, b is 0, so f prime at 0 is 1 minus 0, which is 1, raised to the negative 2 is 1, times 1 is 1. So this is also a 1. Plus, now I have a 1 over 2 factorial here. So I'll write that as 1 over 2 factorial. And my factor here is going to be x minus 2 squared. Sorry, x minus, where did the 2 come from? That's wrong in the line above, too. I bet you caught that a long time ago. That should be a b. And b is 0. So that is x squared. There's my x squared. But what goes in here is f double prime of b. b is 0. F double prime, evaluated at 0. 1 minus 0 is 0. Sorry, 1 minus 0 is 1. Raised to the third, to the negative third is 1 times 2. So that's actually 2. Plus, now let's see, can I move all of this down? I can. Good. My next term starts with 1 over 3 factorial, and then f triple prime at 0. That's going to be my x minus b, x minus 0 cubed. F triple prime at 0, it's this one here, evaluated at 0. 1 minus 0 is 1, raised to a power is 1, times 6. So I'm going to have times 6 here. All right, let's see if we can figure out what the pattern is. Here I have 1 over 0 factorial times, I'll leave that blank for now, times 1, plus 1 over 1 factorial times, I'll leave that blank for now, times x. 1 over 2 factorial, again, I'll leave that blank just for the moment, plus 1 over 3 factorial x cubed. Now, going back to, I don't know, several videos ago, I remember pointing out that once you start to see these numbers regularly, especially in order like this, if I see 1, 1, 2, 3, 5, 8, 13, I immediately think of the Fibonacci sequence. If you don't know what that is, don't panic. It has nothing to do with this class. But the exposure that I have to mathematics leads me to say, I recognize that pattern. It means something to me. The same thing happens if I see the numbers 1, 1, 2, 6, 24, 120, I think is the next one. I think, we're factorials. We're doing factorials here. This is 0 factorial, 1 factorial, 2 factorial, 3 factorial, 4 factorial. That would be 424 times 5 is 120. Yeah, so that's 5 factorial. So that pattern there tells me, we're dealing in factorials here. So I'm going to rewrite these. Instead of having a 1 here, I'm going to write it as 0 factorial over 1. Instead of a 1 here, I'm going to write it as 1 factorial over 1. Here I'm going to write 2 as 2 factorial. And I'm going to write 6 as 3 factorial. And hopefully you can now see why I would want to do that, right? Those cancel, those cancel, those cancel, and so on. Keep in mind we are not dividing by 0 here. This is 0 factorial, which we have identified and defined as being equal to 1. Now, can I determine from this what my nth term should look like? Well, I know it has to start with 1 over n factorial. But then every single one of my f of b's for b equals 0, once I evaluated it, turned into a factorial, right? My f of my original function turned into a 0 factorial. That was 1. This one was 1. This one was 6. Nope. It was 2. That was a 2. That was a 6. And 6 is 3 factorial. 2 is 2 factorial. We said we'll call that 1 factorial and that one's 0 factorial. And you can see there's just an ascending order of integers here, right? Starting with 0. So if that's the case, if every single one of my f of b, f prime of b, the second one was 2 factorial, the third derivative was 3 factorial, then probably the nth derivative is going to be n factorial, and that also matches this other pattern we have in the first several terms. So I'll write that way, and then I have x to the n, x minus 0 to the n, or x to the n, and I can cancel those. If I tidy this up, I get 1 plus x squared plus x cubed plus, and so on, all the way up to x to the power of n. And that is my nth Taylor polynomial for this function. Not for any old function, but for this function, and based specifically at 0. If it was based somewhere else, this would be different, but it's based at 0. I plugged in zeros here, I plugged in zeros here, right? With those restrictions on the problem, this is the polynomial I come up with. Now that's as far as your course pack takes it, but I want to point one other thing out here. This is a really handy, useful little trick. This is a sum, and so there's a way to write this using sigma notation, which I know you've met before, a sum of several things. What is it that is changing? Each one of these has an x in them. This one doesn't look like it does, but it does. Just trust me for a minute. Every single one of these has an x in it. So I can write this as the sum of some x's raised to a power. What's changing is the power. This power is 1, and then 2, and then 3, and then so on up to n, right? So I'm gonna call that power I. That's the thing that's changing. And then I'm going to say, add up all of the x to the power of i's, because we're adding these all up. I can use this notation because we're adding these up. Add up all the x to the i's, starting at I equals, I'll come back to that, and ending at I equals n. Now, this first term looks like it doesn't have an x in it, but it does. It's x to the 0 power. So I'm starting at I equals 0, and I'm ending at I equals n. And if I were to take this, if I did not know what this looked like, if I didn't have that, and I had just been given this, I could say, well, what that means to me is to take x to the power of, start here, and add x to the power of 1, x to the power of 2, x to the power of 3, x to the power of 4, x to the power of 5. How far do I have to go? Well, I don't know, but I know it does end somewhere. It ends at x to the power of n. Now, this version looks like it has more terms in it, but that's because of this ellipsis here, right? This means continue this pattern, the pattern that you see here, continue that pattern until you get to n. Well, I've just written a few extra terms before saying continue the pattern. So this is really the same thing as this. And x to the 0 is 1, so these really are identical. Now, my point in doing this part is I want you to be familiar with this kind of summation notation, not just from the perspective of being able to read it, but also from the perspective of being able to write it, to be able to come up with this notation from something that looks like this. So that's how I've extended this particular one, or why I've extended this particular video beyond what's already in your course pack. All right, now let's take a look at example 3.2. I'm not going to do all of this example because I think the course pack does a reasonably good job of explaining how to do part A, and we've done one just like that. In fact, we've done a harder one. Find the nth Taylor polynomial t sub n for the function y equals e to the x based at b equals 0. If you follow the explanation in the course pack, you'll see that they give you, you can work this out for yourself, they give you the Taylor polynomial 1 plus x squared over 2 plus x cubed over 3 factorial plus, and so on, up to x to the nth over n factorial. Note, first of all, that they left off the factorial here, which doesn't matter because 2 factorial is 2. But we also could have put this over 1 factorial and this term over 0 factorial. And so if we do that, we get another way to write this. We get go from 0 up to n. What you're doing is dividing by n factorial, starting with n equals 0. That's this one back here. Starting with n equals 0, you have 0 factorial in the denominator. And then the next one will be 1 factorial, 2 factorial, 3 factorial, and so on. But also in the numerator, I could change this to a x to the power of 0, and this is an x to the power of 1. Then I get x to the power of n. So this is a much nicer way to write my Taylor polynomial. For part B, we're asked to find the value of n in our Taylor polynomial, right here, so that the difference between the Taylor polynomial and the given function, in other words, the error, is less than 0.01 on the interval -2 to 2. Well, between -2 and 2, I don't actually really like this problem very much, especially this part of it, because the way the course pack goes about doing it is very tedious and computationally heavy, and really kind of requires the use of a calculator. So while it can be done, I'm not really sure I see much value in it. But by way of explanation, I'll just carry on. Now, what they do is they take this inequality, Tn of x, minus the function that we're given, e to the power of x. And this, we need for this to be less than or equal to some number, right? Some value. And so what we're going to do is we're going to set it equal to, or less than or equal to m over n plus 1 factorial, using Taylor's inequality, times x to the power, x minus 0, to the power of n plus 1. And then we're going to make an observation. I'm going to graph y equals e to the x. This is 1. And we're on the interval -1, nope, sorry, -2. -2 to 2. Right, we're given this interval. And you'll notice, if you look at this function, that it starts small, positive but small, and increases forever. But we're only interested in values up to here because we're restricted to this interval, right, to the interval -2 to 2. So that we could effectively erase the rest of this function. So we're not interested in that, and we're not interested in this part down here. Erased a little too much there. So we're only interested in that part of the function for now. And so if you look at this, you can just make the observation that this is the maximum value. This thing right here, this point right here, is as high as this function gets in this interval. What is that point? Well, it occurs at x equals 2, and its value is e to the power of 2, because this is the function y equals e to the x, right? So my m value then is just e squared, e to the power of 2. It's a constant, but that's what m is. It's a constant. Now you might be wondering how I was able to jump straight in here and find m without taking any derivatives. Well, I'm working with the function e to the x. Doesn't matter which derivative you're on, the derivative is the same as the original function, right? So this is the nth derivative. Where am I? I'll just use this. This is the function, but it's also the first derivative of the function, and the second derivative, and the third derivative, and the nth derivative. This is the nth derivative, and so m is the next derivative, the n plus first derivative, n plus 1th derivative, but that's e to the x as well. So I'm just graphing e to the x because it's the n plus 1th derivative and looking at its maximum value. Now, the other piece of this puzzle here is this x to the power of n plus 1. Well, since we're trying to make this as big as possible, so as to make the error as small as possible, we want to find the value which, when raised to a power, gives you the biggest value here. And any number raised to a power, the result is going to be bigger if the number you're raising to a power, the base, is bigger. So we'll take the base to be 2. So let's change that x to a 2. Now in this case, we were asked to find n so that this error was less than 0.01. And your course pack goes about plugging in n equals 1, and then 2, and then 3, and then 4. And the point is to try to get this error to be the same as this error right here, to be less than 0.01. So we want this value here to be about 0.01 for some value of n. And your course pack goes about plugging in, first 1 and then 2, and they try to find the n value that will give this thing here a value of something around 0.01. And it turns out they get to n equals 9 because at n equals 8, this value is just over 0.01, and at n equals 9, it's actually quite well under 0.01. So they say from that it's sufficient to take n equals 9. The answer to this question is n equals 9. Now, I don't really see the point in just calculating this for various different values of n. I mean, what if that turned out to be 17? Would you know before you got to n equals 15 that you were going to only going to have a couple more to do? It's just such tedious work. I suppose another way to do it would be to plug this into Desmos and use perhaps a or something instead of n for these two values here, and then let the slider do the work for you, finding the value of n for which this thing returns a height. That would be a constant, but it would be a changing constant, right? It would be a horizontal line that would move up and down the screen. Find the value of n for which the horizontal line went through y equals 0.01 or something just under that. That would be another way to do it. Beyond that, I don't really see the point of this exercise. But, it's there, so now we've talked about it. And I think I'll actually leave part C alone altogether. You're welcome to look at that part and see what it says, but I'm not terribly concerned about whether or not that particular instance or that particular use of Taylor's inequality comes into play for us. But with that, that brings this section pretty much to an end. We've talked about now through the course so far, we've talked about the known Taylor polynomial that we had met before, the first Taylor polynomial, which we previously called the tangent line or the linear approximation. And then we talked about quadratic approximation, which was better than linear approximation, but not really all that much better. And then in this past section, we've been talking about higher order approximation, third and fourth Taylor polynomials, but we can also talk about kind of a generic nth Taylor polynomial. In every case, there's a certain amount of error involved. And we've talked about what the error looks like, the form that it comes in, the sort of formula that we have for it. And for the nth Taylor polynomial, the error is called the Taylor's inequality. So that pretty much does it for the first half of the content of this course. In the next video, we'll be talking about Taylor series.